So, today I will demonstrate experiment on photoelectric effect. Aim of this experiment is basically determine the Planck's constant from the stopping potential measured at different wavelength. And second aim is study the effect of the incident intensity of the photocurrent and the stopping potential at a fixed wavelength. So, basically we will find out the Planck's constant. This is the universal constant that we will find out from this experiment. Also we will study the effect of light intensity on the photocurrent and corresponding stopping potential at a fixed wavelength. So, background, this is a historical background is there for this photoelectric effect, as you know. So, basically birthday of quantum physics is 14th December 1900, 14 December 1900. Okay. So, E equal to h nu, h is a so this relation was given by the Planck. So, Planck introduces a new fundamental constant h to explain black body radiation. Okay. So, that is why this was the starting of the quantum mechanics, quantum physics. So, that is why we take this date 14th December 1900 as the birthday of quantum physics. So, but this photoelectric effect was explained by Einstein in 1905 after 5 years. So, what was the importance of this Planck's equation E equal to h nu as well as the Einstein's explanation or Einstein's equation for the photoelectric effect? What was the importance at that time? So, at that time people are only familiar with the classical concept. Okay. So, classical concept never allow to think that wave may also behave like particle. That is the Planck's hypothesis. Particle may behave like wave, that de Broglie hypothesis. Position and momentum of a particle cannot be measured accurately simultaneously. So, Heisenberg uncertainty principle. Energy of wave is related with the frequency and the energy is quantized, that is E equal to n h nu, h nu, 2 h nu, 3 h nu, okay, or h nu 1, h nu 2, h nu 3, nu 1, nu 2, nu 3, these are different energy. Okay. So, this whatever I mentioned 4 points here. So, classically we cannot think these facts. Okay. So, these new concepts, but it happens because these are hypotheses. Based on that many physical phenomena was explained. So, that means these hypotheses are real. It is not just hypothesis generally verified with the fact, okay, with the experimental observation, etc., etc. So, thus the credibility of this hypothesis, initially it was assumed, and if it can explain everything, okay, then it's a accepted assumption. So, that we tell hypothesis. So, these new concepts are basically quantum concept. It is not classical concept. From classical concept we cannot accept them. So, it is a new area of science, new area of physics. Okay. So, that basically quantum concepts. So, these are the things basically beginning of the quantum physics. Okay. So, in case of interference and diffraction of light, we have seen those phenomena are explained from the wave property of light, right, and there the intensity distribution of uh, of interference effect or interference fringe, diffraction fringe. Okay. So, that intensity distribution, that was basically explained taking the intensity as a square of the amplitude of the wave. Okay. Square of the amplitude of the wave. So, when two waves are meeting, interfering, or there is a diffraction, so then following the superposition principle, so we add the displacement of individual one. Okay. So, then we are getting the resultant amplitude of the resultant wave. So, intensity square of that amplitude. Okay. In that amplitude there may be phase term also. Okay. So, that we have seen for interference and diffraction. So, amplitude square of the light wave gives the intensity. So, intensity of light is nothing but the energy of the, and also intensity of light is nothing but the energy of the light. Okay. More intense light, more energy are there, it is supplying more energy. So, that is the concept we used for the explanation of the interference and diffraction property of light, and that basically is the wave concept of light. Okay. But this concept of energy of light was unable to explain the photoelectric effect. What is photoelectric effect? So, what was the observation basically? So, on a metal surface, if light falls, it can be say monochromatic light, either red light or blue light or green light. That means their wavelengths are different. So, if you just consider one by one, so light is falling on this metal surface, the wavelength of this light is lambda 1, red one. Okay. So, wavelength is higher than the green and blue one. So, higher wavelength light is falling on this. Now, when light is falling on it, so electron, so this light is absorbed by the metal electron, free electron, okay, and it come out from the surface. So, it come out from the surface. So, these electrons we tell photoelectron, because these electrons are generated from the due to the photon, due to the light. Okay. That time photon concept still was not there. So, the light. Okay. So, now if you put a anode, and apply positive voltage, okay, so these electrons will move towards the anode, and these electrons will reach to the anode, and we will get anode current. Now, we are observing this anode current. So, more electrons will reach to the anode and more current we will get, Okay. So, for a particular anode voltage, we will get current. So, that current should depend on the intensity of light, on the intensity of light. Okay. So, if I take red light and then if I increase the intensity of light, then what will happen? I would expect, we are expecting that we will get more and more currents, because more energy on falling on this metal surface. So, more electrons will come out and they will reach to the anode and we will get more current. Okay. So, it should be independent of the color of the light. So, if I take white light, I should get the same thing. If I get, say, monochromatic light, say red color, I am doing experiment. Then if I take this blue color, then I am doing experiment. So, for same intensity of light, that intensity I am talking about the square of the amplitude of the light wave. So, that is the intensity of the light. Okay. So, we will expect the same current, for all wavelength for a particular intensity. Okay. If we increase the intensity, so current should increase. Okay. So, it should be independent of the wavelength of the light. It should depend only on the intensity of the light. Okay. So, that was the concept. That was the result people are expecting, but the result is different. What was the result? The anode current increases with the intensity of light for light of lower wavelength. Okay. And for higher wavelength, lower frequency, sometimes the anode current is 0, whatever the intensity of the light does not matter. Okay. So, the result is just showing opposite. Sometimes it does not depend on the intensity of light. Whatever the intensity of light, no electrons are coming out. It depends on the wavelength of this light falling on the metal surface. Okay. So, in this experiment, whatever observation, that is basically that anode current means the number of electrons. So, sufficient anode voltage is given, it is assumed that all electrons will reach to the anode. Okay. So, this result is showing that the number of electrons will emit from this metal surface, it does not depend on the intensity of light. It mainly depends on the wavelength of the light, frequency of the light. So, why it should depend on the frequency of light? Why it should not depend on the intensity of light? Okay. So, that was the puzzle, that from classical concept, this result was not possible to explain. So, that's the difficulties people face, and then this Einstein came forward, and Einstein in 1905 he considered the particle nature of light, that is basically called photon, and energy of each photon is h nu. He considered the energy of each photon is h nu. Okay. The intensity of light is considered as the number of photons present in the light beam. Okay. So it's a completely different concept than the wave concept of light. Wave concept, when it is wave concept, then amplitude plays the role. Amplitude is related with the energy. Okay. So Einstein considered it, the light, as a particle. It's a just like cathode ray, this beam of electron. Beam of electrons, that is the cathode ray. Similarly, this light ray is the basically beam of photons. Okay. So it's not wave. Wave gives the continuous, this sense of continuity, right? So something is continuously moving, and photon or particle, it gives the individual entity. So they are moving in a series. Okay. Then we tell this, that's beam of photons. So intensity, how many photons are coming or falling, so that will be taken as the intensity of light. And energy of the light is basically energy of each photon, and this total energy you can take summation of them, of course. So that was the, so basically wave concept of light could not explain this experimental observation. So Einstein considered the particle nature of the wave. Of course, he took this Planck's energy quantization, E equal to h nu. Okay. He took that one and used for explaining this result. So that's why for a particular metal there is a work function, means electrons are free in the metal, but it cannot come out from the surface. Okay. So you need minimum energy to release the electron from the metal surface. So that energy is basically called the work function of the surface of that metal. So there is a work function which prevent electron to leave the metal surface. So minimum energy of photon, that is say h nu 0, equal or higher to the work function of the metal surface. So that is the work function W, is required to eject electron and get anode current. Okay. So photon of lower energy, say h nu, where nu is less than nu 0, cannot eject electron whatever the number of photons falls on the metal surface. Okay. So these electrons basically they absorb one photon. Okay. So when they will absorb this one photon, that the electron is getting basically one, so energy h nu. If that energy h nu is less than work function, it cannot come out. So it does not matter how many photons are falling on that. So that's why, so h nu is c by lambda. So that means electron will come out from the surface or not, it depends on the wavelength of the light. For higher wavelength, lower frequency, you will not get electrons ejected from the surface of metal, and there will be no anode current. So, if higher wavelength, lower wavelength, higher frequency, so energy h nu will be higher than the h nu 0, okay, or higher than the W work function. So, then each electron will absorb this one photon. So, it will get h nu energy which is higher than the work function. So, it will come out, it will overcome that work function barrier, surface barrier, and it will come out and it will have some additional energy. So, that energy will act as a kinetic energy. Okay. So, this concept of photon with energy h nu and intensity with number of photons leads to the equation h nu, the energy of the photon, equal to work function plus half mv square. This is the kinetic energy of the electron, ejected electron. Okay. So, this called the Einstein equation of photoelectric effect. Okay. So, using this equation, it was nicely explained the experimental fact, which was not possible to explain using the wave concept of light. So, h nu depends on the wavelength of light, of course, and W depends on the particular metal surface. Okay. So, for a particular light of wavelength lambda and for particular metal having work function W, the kinetic energy of photon or its velocity of electron will depend on this h nu minus W, right. So, the kinetic energy is determined using the stopping voltage. Okay. So, whatever the kinetic energy of the electron, so with this kinetic energy, electron basically will move towards the anode and it will reach towards the anode. So, without giving any voltage, to anode, we may get anode current, okay, due to the kinetic energy of the electron. Now, if we apply, so what is that kinetic energy if we want to measure? So, what we can do in anode, we can apply negative voltage. We can apply negative voltage, then this electron will be deaccelerated, okay. So, it will feel repulsion, so it will be deaccelerated. So, if you increase the negative voltage of the anode with respect to the cathode, cathode means metal surface with respect to the cathode surface, okay. If you increase the negative voltage of anode, so what will happen? On time will come that no electron will be able to reach to the plate. So, the plate current will be 0. So, the voltage at which the plate current becoming 0, so it is a, so that we taken as a stopping voltage, okay, and corresponding potential energy is EV, okay. So, opposite energy, that is EV, so that energy will be equal to the, kinetic energy of the electron. So, a negative bias with respect to cathode is applied to the photoelectric cell anode. This deaccelerates the electrons and thus decreases the photoelectric current intensity I. So, the value of the bias where no electron reaches the anode and I become 0 is called the stopping voltage V. So, that is why, that is what I explained. So, thus the electrons will reach the anode as long as their kinetic energy is equal to the potential energy associated with the applied reverse bias. That's I told that EV, the potential energy EV equal to half mv square. So, that half mv square equal to basically h nu minus w. Here additional minus phi I have written. So, this phi is basically additional contact potential occurs at the surface of the anode. So, when from metal surface electron just cannot come out. So, there is a barrier. So, that is the we tell work function W, and when that is falling on the anode surface, okay, so that electron will in contact with the anode surface. So, that there will be contact potential, means again to that electron cannot enter to the anode, cannot penetrate the anode surface. So, it has to spend some energy. So, it will feel some barrier there also. So, that we are telling contact potential. So, that we are is phi. So, whatever the energy of the light h nu photons. So, the energy will be spent for the work function of the metal surface, for the contact potential of the anode surface. Okay. So, then the balance rest of the energy h nu minus w minus phi will be the kinetic energy of the electron, and at stopping potential V, stopping bias V. So, this kinetic energy will be equal to EV. So, you can find out V equal to stopping potential equal to minus W plus phi by E plus H by E nu. So, for a particular metal or anode, so this term is basically constant. H by E, that also is a constant. So, they are independent of frequency we are considering. So, this here Y equal to mx plus C. So, this is the equation of straight line. So, Y means here V, stopping potential, and X means here nu. Okay. So, M will be the slope. So, from the straight line, so if you plot V versus frequency, then you will get a straight line, and from that straight line if you find out the slope, so that slope equal to H by E. So, E is supplied electronic charge, okay, it is supplied 1.6 into 10 to the minus 19 coulomb, okay. So, that is supplied, then you can find out from the slope, and from known E, known value of E, you can find out H, okay, Planck's constant. So, this is the first part of the experiment, and second part of the experiment is basically I think, yes. So, basically we will for a particular wavelength, and particular intensity of the light. Okay. So, what we will do, we will increase the distance between the source and photocell. Okay. So, light will fall on the cathode. So, we will increase the distance between the cathode and the source. Okay. So, when we will increase the distance, then that means the intensity of light which is falling on the cathode of photocell. So, that cathode, that intensity will be lower, will decrease. So, that way basically increasing the distance of light source from the cathode from the photocell will change the intensity of light on the cathode surface, and for a particular wavelength of course, and will note down the change of the anode current. Okay. So, how anode current is changing with the intensity of light for a particular uh, frequency or for a particular wavelength. Okay. So, that is the second part we will do. So, for this experiment the electrical circuit we will use, this is the electrical circuit. So, we have a it's a compact one, you know, we have a, it's the photocell, we tell it's a photocell. In photocell there is a photocathode and there is a anode. Okay. So, light will fall on this cathode. Now, electrons will emit from this photocathode and it will reach to the anode. Okay. So, then we will get basically photocurrent, we will get photocurrent, and that current we will measure using the nanoammeter. Okay. Nanoammeter. Now, to study the behavior of the current, photocurrent with respect to the voltage applied to the anode with respect to the cathode. Okay. So, whatever this we are telling, negative voltage we are applying, so retarded potential we are applying, so stopping potential we are applying. Okay. So, how much voltage is applied, so that from this voltmeter we will get. Okay. So, it is the parallel connection with this one. Okay. So, how much voltage we are applying? So, basically we are applying from this setup. So, we have a DC power supply of constant voltage, say we will take here around 2 volt. Okay. So, now this is the, so this voltage will drop across this resistance, So, this is the rheostat basically. So, we will vary the resistance, so then voltage, so this end and this end. Okay. So, that voltage drop across this part of the resistance will give the voltage to the, so that way this, from this changing the resistance here, moving this rheostat knob, we can vary the voltage. How much voltage we are varying or applying, so that we will get from voltmeter. So, basically what experiment we will do, we will change for a particular wavelength of light, we will choose to fall on the photocell, and we will apply initially we will apply zero voltage. Okay. So, we will get maximum photocurrent, because here we are applying negative voltage, now voltage is 0. So, maximum voltage we will get now, maximum current we will get. So, maximum electrons will reach to the anode. Now, we will increase the voltage, negative voltage. Okay, negative, it is attached with the anode, negative voltage. Okay, and we will change this voltage, and we will note down this current. Okay. So, current will decrease and we will get a particular voltage where this current will be 0. So, that voltage is basically we will take as a stopping voltage, whatever the equation we have used. So, for different wavelength of light, different frequency of light, we will find out the stopping voltage, okay, from this measuring the photo current. Okay. So, this is the experiment, and another experiment is actually we will apply particular voltage, okay. Uh, so, we will choose particular wavelength. Now, if we increase the distance of this light source from the photocell, so intensity of light will decrease on this photocell. So, thus we will change the intensity of light falling on the photocell, and we will see how current is changing. Okay. So, there are table for that, for noting down the data, experimental data recording. So, least count of voltmeter, least count of ammeter, separation between the lamp and here filter, basically the source. We will use filter because we have to get monochromatic light, okay, of different wavelengths. So, we will use filter. So, we will take that from filter, monochromatic light is going. So, filter as if that is the source of light, monochromatic light. So, at front of the photocell. Okay. So, we will note down this, because these are important, because this will keep the intensity constant for a particular experiment. Now, so determination of stopping potential, as I mentioned. So, you take different wavelength, and for each wavelength you note down the change the voltage and corresponding current, and find out that which voltage the current becoming 0. Okay. So, that is we will continue, we will use I think 5 or 6 wavelength for this experiment, and then we will plot them. So, we will get stopping voltage for different wavelength, then basically we will plot V versus frequency nu. Okay. From wavelength you can calculate nu, frequency, and we will find out the slope, and hence H, Planck constant, right. So, second work is dependence of the photocurrent on the intensity of light. So, separation between lamp and filter. Okay. So, we will change this distance between lamp and filter. Okay. So, intensity of light on the photocell will decrease. So, bias in voltage, some voltage will be given, okay. Some voltage will keep fixed. Okay. Now, photocurrent will note down, just changing this distance, Okay. So, this way we will continue to see the how this photocurrent or ejection of the electron from the cathode surface, how it changes with the intensity of light. Okay. So, we will draw graph and we can see the nature. Okay. So, error calculation for the Planck constant. So, H by E equal to slope of the V versus nu curve. So, slope how you will get? You will get 2 voltage corresponding to frequency, okay, difference of frequency and difference of voltage. So, V1 minus V2 by V nu 1 minus nu 2. That is what we will take from the graph, and that is the slope. So, H is V1 minus V2 by nu 1 minus nu 2 into E. So, take log and then find out, because E is supplied one. So, no error from that E, and so you will get basically 2 del V by V1 minus V2, and this also will not contribute because we are calculating nu from the supplied lambda. So, we are not measuring. So, that is why this will be the most probable error for the measurement of H. Okay. So, that is the description of the experiment I made. Now I will demonstrate the experiment in next class. Thank you.